Dear colleagues, dear friends, this presentation is dedicated to the precession. Precession is a motion of a rigid body having 3 degrees of freedom. We will see the behavior of a bicycle wheel which having motion like a gyroscope. So having a spin, having a precession and having a tilting motion. In the first part, we make some observation to understand what is the precession. Then we will amuse ourselves with some formulas and we try to give some explanations. Eventually, we will deepen our study by introducing some more physical parameters like tilting angle and also friction. Let's start with the first experiment. So the wheel rotates horizontally. In this case, there is no precession. So the wheel is steady, it's rotating along its axis and is keeping the position horizontal. In the second experiment, the wheel is kept vertical, it's spinned clockwise first and then is left free and it makes a precession also clockwise. In the last experiment, the same wheel is also kept vertical, but it's spinned counterclockwise. And in this case also there is a precession, but the precession is opposite, is counterclockwise. We try now to give an explanation of what is happening by using the theory. The second cardinal equation of the dynamics says that the momentum of the external forces m0 is equal to the derivative of the angular momentum versus time L minus the vectorial product between the velocity of the momentum pole and the impulse of the system. But this part is 0 in our case. The momentum we can express as the product of the weight times the arm and sinus theta. And this is directed along I-axis. How to express the angular momentum of a rotating wheel? It is the momentum of inertia I times the spin velocity omega s, and it is directed as the wheel axis k, as in the picture here. The reference ijk is integral with the wheel, while the vertical axis zeta is fixed. Also, the derivative of the angular momentum is made of 2 parts. One is parallel to k and one is square to k, because the derivative of the versor is given by the Poisson theorem when we introduce the angular velocity of the reference system, this big omega. For definition, we call this rotation precession of the system, omega pre, and is directed along zeta axis, assuming theta constant. Finally, omega product k is directed as I-axis, as well as the momentum of the weight. The motion equation has 2 components, one along k-axis and one along I-axis. The component along k-axis is saying that the omega spin is constant, and the second is saying that the omega precession, the one we want to find, is given by this formula. So it's the ratio between the product of the weight and its arm and the momentum of inertia of the wheel and its spin velocity. Interesting is if spin rotation direction changes, also precession direction changes, as we have seen in the experiment. To convince you, I made some measurement by the experiment and I considered the both velocity, omega speed and omega precession in the real case, and the omega precession given by the formula. As you can see, there is an error, but it is small. What we observe in addition is that during the time, the omega spin is decreasing, and parallelly, the omega precession is increasing. And this is also due to the friction, which is not considered by this equation. We will see in the next slide a more accurate model to describe also the friction effect. Another important effect of the friction is that the tilting angle theta is not constant, but it is increasing during the motion. We have recorded here some different positions at every round. The mechanical energy during the rotation is not conserved. And we are going to add two additional equations to describe the motion more in detail, starting from the energy dissipation. What is the mechanical energy? It is the sum of the kinetic and the potential one, being the kinetic half of the scalar product between the angular momentum and the angular speed of the system omega. And the potential energy is the work of the conservative forces, in this case, the momentum of the weight times its rotation with minus. And we write here the three components of omega using the 3 degrees of freedom of the system, which are alpha, spin angle, phi, the precession angle, and theta, the tilting angle. And we find the expression of omega along the reference relative to the wheel axis, which is ijk. We remember the more complete definition of the angular momentum, which is equal to the product between the inertia tensor and the above omega speed. We introduce the inertia matrix 3 times 3, having only 3 components because of the symmetry. Actually, the wheel has only 2 different inertial momentum, I0 and I. One is along the k-axis and one is square to it. Let's see the expression of the mechanical energy, which is not constant during the motion as told before. Its delta is equal to the work of the dissipative forces, which are the friction momentum unknown and the spin angle L alpha. So the product in between them is equal to the difference of mechanical energy. And thanks to this equation, we can find the value of the friction momentum having all the remaining variables experimentally metered, and we find 0.045 Newton per meter. The third and last equation is the projection along the vertical axis zeta of the second dynamic equation. And here the weight disappears because its momentum is directed as the axis I. And with some development, we come to this expression where at the second member appears again the friction momentum and an integral in the unknown variable theta. This is not elementary solvable because theta is a function of time. Okay, the 3 equations are the one which have already been seen in the beginning, the mechanical energy, and the angular momentum, its vertical component. It is actually a system of differential and integral equations, function of time. The unknown functions are 3, alpha, phi, and theta. The initial conditions are also 3, omega spin, which is starting spin, tilting speed 0, and tilting angle, starting angle, as displayed here. We can solve it numerically using this approach. We prepare a table, and in the first column we fill the time 0, the starting condition, and then all the values which are known in the yellow column. The ones represented in this table are coming from the experiment, so are also known. And we write all the corresponding functions in the first row of the table. we calculate phi point, which is coming from the first equation, and then we calculate the first member and the second member of the equation number 3 as far as the first member and the second member of the equation number 2. In this case, everything is 0, but just for the first step. If we come to the second step, we can see that the values are changing. And for alpha point and phi point, we are using as guess value the same values as for time 0. But we notice that the corresponding values here are not equal. So it means the guess values are not correct. What we need to do? We need to change the guess values iteratively till when the corresponding first member and second member of equation 3 and first member and second member of equation 2 are the same. We repeat the procedure for every time step, in this case till 25 seconds, and when we have done, we get this big table. The blue columns must be equal as well as the red one in order to satisfy all the conditions. Eventually, we can check the experimental data versus the simulation ones. And we find that they are quite similar each other. So we can predict the behavior of the wheel, we can predict how the alpha point, so which is the spin velocity, is changing, how the precession speed is changing, and also how the tilting angle is increasing. And this is really very comfortable because our model is matching the reality. Thank you very much for your attention. Bye bye.